It was asked during the break, what happens if you consider letting x approach other values, like for example 4? And for this example, the answer is 1. You know, what you would expect by looking at the picture. Nothing too strange is happening at other values of x. For example, 4. If you let x approach -4, the answer would be -1. Right? It's just that the interesting thing, the jump discontinuity is happening at 0, and that's why 0 is being focused on. You have another example involving something called the floor function, also known as the greatest integer function. Here's its formula. I put the word formula in quotes because it's not really a formula in the usual sense. It's just a bunch of symbols. What in the world is that? All 1, 2, 3, 4, 5 of these symbols are used by various people to mean the same thing. I usually prefer using this one, so that's why I put that one first. That's my preference. Some books, maybe including ours, use that one. Some books use this. Some books write floor of x. Some books and calculators use int of x. What in the world is this? It's just a function whose graph looks like this. It's piecewise defined with really infinitely many pieces. It's the greatest integer in any given number. What does that mean? It essentially means to round down to the nearest integer for the output. So if you plug in a number like 2.1 into this function, x is 2.1, the output is 2. You've rounded the answer down to 2. The output is the rounded down version of the number. But that works even if the number is closer to a bigger whole number. For example, if you plug in 2.9 into this function, the output is still 2. You still round down to 2. It's only when the input gets to exactly 3 that you jump up to an output of 3 right there. For extra emphasis, I could have also drawn in here some filled in dots to emphasize those are part of the graph. So again, it's not a formula in the usual sense. It's just a special symbol that means round down to the greatest integer less than the given number, less than the input. It's a little funny for negative numbers. If you plug in -2.1, technically when you round that down to the greatest integer less than -2.1, it's really -3 for the output. The output is -3, not -2. Think about a number line and rounding down by moving to the left on a number line. The input is -2.7, the output is still -3. If the input is -3, the output is -3. If the input is -3.1, the output is -4. This is actually a pretty useful function in certain circumstances. It's also kind of fun to look at. It's like a big staircase. It's an infinite staircase going on forever and ever. What about limiting values? Well, here I am considering, first of all, an atypical or a non-interesting case, you might say. If c is not an integer, if it's like 2.1 or 2.7 or even pi, oh, this is a mistake. That's a typo. Ignore that. Don't write it. It does not equal c. Sorry. It equals the greatest integer less than c. If I was going to write this, I should really put the symbol there. If c is not an integer, then f of c is the greatest integer in c, and that's also the limit as x approaches. That's wrong. You can make it correct by putting the greatest integer symbol. It equals f of c. If n is an integer, whole number, positive or negative, then the limiting value as you approach n from the right is f of n, and that equals n. On the other hand, if you let x approach n from the left, the limiting value is n minus 1. Like if you let x approach 2 from the left, the limiting value is 1. Function values are 1. I'm not letting x equal 2 when I think about that. Because the left and right hand limits are not equal to each other, the two-sided limit does not exist for any integer n. And again, there's a typo. This should really be the greatest integer in C, which equals f of C. Okay? So again, kind of a strange function. It's actually more useful than you might guess in certain circumstances. All right, we're about to get into the theoretical stuff. Might be good if you're taking notes just to paraphrase what you see here and focus more on what I say, focus more on listening to me. That might be better. I'll put this in a shared folder later this afternoon. Definition of the limit of a function at a point. I will start intuitively. Maybe this is worth writing down. Suppose C is a number, and that a function f is defined near C, but possibly not at C. Maybe the graph has a hole in it at C, like the examples we considered. Let L be some other number. We say that the limit, which is a two-sided limit here in this notation, as x approaches C of f of x equals L, which you can also read as f has limit L at C, if you can make the outputs of the function as close as you like to L by making x as close as necessary to C without actually equaling C. Here's the way I wrote it. We can make the outputs f of x as close as we like to L by taking inputs x sufficiently close to C, regardless of what happens to f of x when x equals C. It may not even be defined in C. F of C may be undefined, as it was in many of the examples we looked at. Three rational function examples. As a definition, this is not good enough. Definitions in math need to be precise. And words like close and sufficiently close are not very precise. What does that mean? Here's a precise or rigorous definition. It's pretty strange to look at, okay? I'm going to warn you here. It takes a while to get used to. Its purpose is to precisely define what a limit means, and therefore also be used in proofs. Here's the way it goes. We say the limit is true, the limit as x approaches C of f of x equals L, if for any number epsilon greater than 0, that's a Greek letter, no matter how small, there exists a number delta greater than 0, chosen sufficiently small, so that when this is true, this is true. You can see what I mean when I say that's difficult to understand. The first thing I should say before we try to understand this and use it is to talk about what the absolute value of a difference represents. The absolute value of the difference of two numbers, A and B, represents the distance between them on a number line. Distance between the number A and B on a number line. The number line could be horizontal, and so it could be a horizontal distance. It could be a vertical number line, like a y-axis, and so it could be a vertical distance. Any number line you draw, making the points on that number line, the whole number values, say, equally spaced, this represents the distance between them. If you don't believe it, try examples. What's the distance between 5 and negative 17? Well, it's 5, the absolute value of 5 minus negative 17. Absolute value of 22, which is 22. Notice the answer And the formula is symmetric. I could switch around the roles of the 5 and the negative 17, and I'd still get an answer of positive 22. And indeed, if you draw a number line, here's negative 17, here's 5, 0 would be like right around there. The distance between them is 22. Either way you write it, a minus b or b minus a, it still represents the distance between a and b on the number line. And again, you can make your number line horizontal, you could make it vertical. You could even make it slanted for all you care. We don't do that, but we could. It still represents that distance. So, coming back to this definition, when we say that the absolute value of x minus c is less than delta, we're saying the distance between x and c is less than delta. It's also bigger than 0, which means x does not equal c. That's all that means. Because we don't care about what happens to the function at c. That's why we have it. The function might have a hole in its graph there. And here we have another absolute value difference. This is the distance between the output of the function f of x and this limiting value L. I can make this distance as small as I like, less than any given epsilon, by choosing x sufficiently close to c. This is the measure of sufficiently close. Let's see how this plays out in a proof. And as we do the proof, I'll also draw pictures to help us understand. This limit proof that I'm about to do is what you want to mimic for that graded assignment problem. Okay? But again, like I said before class started, when you do it on the graded assignment, don't write it down with the exact same words I use. You can use the same structure, and you want to get the same point across, but use a little variety. Try to explain it in your own words. That'll help you understand it better anyway. What are we going to prove? We're going to prove that the limit as x approaches negative 3 of the function negative 4x plus 5 equals 17. As we look at the proof, I'm going to be referring to a picture that I'm drawing on the board here. This is a linear function. F of x equals negative 4x plus 5. Has a graph that's a straight line with a slope of negative 4 and a y-intercept of 5. It goes to the point 0, 5. It would also go through the point 1, 1. Because the slope is negative 4. That'd be the point 1, 1 there. It also goes to the point negative 1, 9. That point has coordinates negative 1, 9. It goes to the point negative 2, positive 13. That point there has coordinates negative 2, positive 13. And if you go up by another 4, in the y value, and down by another 1 in x value, it goes to the point negative 3, 17. So it's a straight line through those points. Pretend this is a straight line. Okay? 17 is the function value at negative 3. And it's also the limiting value as x approaches negative 3. That shouldn't be surprising because the function is continuous. It's a nice linear function. Its graph is a straight line, no holes in it. So this shouldn't be surprising. The picture is not a proof. So we're going to give a proof. Here's how you do it. This first sentence, you can probably use the exact same wording. You start by saying, let epsilon greater than 0 be given. Epsilon is my measure of how close I'd like to be to the limiting value 17. L here is 17. On this vertical axis here, it's right there. There's L equals 17. Epsilon is a measure of arbitrary closeness to 17 in this case. It's a distance. You can think of it as a distance on this vertical y-axis. I'm going to redraw the picture over here a little bit bigger. Imagine going up epsilon from 17 to the point 17 plus epsilon. Epsilon's a Greek letter, if you haven't figured that out. You could go down from 17 by distance of epsilon to the number 17 minus epsilon. Epsilon is arbitrary. It could be super tiny. It could be 10 to the negative Google power. It could be super duper tiny. Of course, I haven't drawn it to be super duper tiny, but it could be. It's a measure of arbitrary closeness to L, to 17. The definition, if we go back to that, the definition says, no matter what epsilon is, no matter how small, even if it's 10 to the negative Google power, I can find another number, delta, possibly much smaller than epsilon even, sufficiently small, so that if the input x is within delta units of c, c is negative 3 for us, then the distance between the output and L is less than the given epsilon. Let's look at this picture again here. Can I choose delta sufficiently small? That distance is delta, a horizontal distance. So that if x is in this interval somewhere within delta units of negative 3, possibly not equal to negative 3, that when you plug in inputs in here, the outputs are all within epsilon 17. Imagine going to this picture here. If this is negative 3 minus delta down here, and this is negative 3 plus delta down here, that's hard to see. That one says negative 3 minus delta. This one says negative 3 plus delta. Kind of hard to draw down here. If my inputs are in there, then the outputs, are they all within this distance of 17? If you look at the y coordinates of these points, are they all within epsilon 17? With this picture that I drew, it looks like I didn't pick delta small enough, because there are some points where the output is further away from 17 than epsilon. So in that picture, I didn't quite make it smaller. But if I made delta smaller, if I made these 2 points closer together, then for those inputs, say in a smaller interval, the outputs would be between 17 minus epsilon and 17 plus epsilon. So the question is, how small should delta be? And that's based on some scratch work. And here's the scratch work. You don't have to include the scratch work in your proof. Think about this difference and say to yourself, I would like to make this less than epsilon. That's the kind of thing you think about when you say it, when you do this. I would like to make this less than epsilon. How? Well, simplify it first. Plus 5 minus 17 is minus 12. How can I make that less than epsilon? Less than an arbitrarily small number? Well, you're missing something if you only think about it that way. You need to realize that x needs to be close to negative 3. If I factor out a negative 4 like this, I have an expression there, x plus 3, that equals x minus negative 3. And the absolute value of that would be the distance between x and negative 3. It's a property of absolute values that I can now take the absolute value of a product, like this times this, and take the product of the corresponding absolute values. And let me go ahead and write this one that way. And the absolute value of negative 4 is positive 4. I can simplify this thing to this, and this is good because I can make this whole thing less than epsilon by making this thing small enough. I want this to be less than epsilon, that's what I want. How can I make that happen? Divide both sides by negative 4. I can make that happen as long as the distance between x and negative 3 is less than epsilon over 4. The logic will work backwards. And this, therefore, is what the delta is. Let's see how the logic works on the proof. So the next sentence I say, choose delta to be epsilon over 4, which is positive. If you only look at the proof, that feels like something pulled out of a hat. Like, why did you choose delta to be epsilon over 4? What a weird thing to do. It does seem weird, but it's based on that scratch work. It's because I knew based on the scratch work that I should choose delta to be epsilon over 4. Okay? You will have to do similar scratch work. Again, you don't need to include the scratch work in your final proof. The scratch work is on a separate piece of paper. What do I have to do now? I need to assume x is within delta of negative 3, and follow this logic to ultimately show this is less than epsilon. Suppose the number x satisfies this condition. What is that saying? Always remind yourself what that's saying. That's saying the distance between x and negative 3 in the number line is less than delta. Think about this picture. The distance between x and negative 3 is less than delta. It's in this interval somewhere. Where delta happens to equal epsilon over 4, because that's how I would define it. Now you just need to tease out what this means. Multiply everything by 4, and you can write this exact same string of inequalities this way. By the way, the assumption that this thing is bigger than 0 is not really relevant for this particular problem. I'm putting it in there because sometimes it's relevant. And in particular, it would be relevant if for this function we decided to have a discontinuity at at negative 3. Just to do it. Say it was undefined at negative 3. Then I would need this condition. But it really doesn't affect the rest of the proof. The key thing that affects the rest of the proof is this inequality right there. And again, to get from there to there, I just multiplied everything by 4. That is okay to do. 4 is a positive number. It doesn't change the direction of the inequalities. But what does that mean? Now come back to your scratch work and essentially redo it. Hence, basically hence means therefore. Hence, the distance between f of x and L is this, which simplifies to that, which simplifies to this, which is less than epsilon. That actually does it. That's really the end of the proof. Praise the Lord. Once again, we're in a situation where part of the reason this is difficult is you don't know how to start. There's 3 big reasons why proofs are difficult. People don't know how to start, they don't know how to end, and they don't know how to get from the beginning to the end. All 3 of those are problems for people. Difficulties in doing proofs. You know, if I didn't tell you to start this proof by saying let epsilon greater than 0 be given, you wouldn't know to start that way. If I didn't tell you that showing this is less than epsilon means you're done, you wouldn't know when you're done. And if I didn't show you some scratch work and help you see how the scratch work comes out in the proof, you wouldn't know how to connect the beginning from the end. It's a hard thing, okay? You should be consoled by the fact that Newton didn't learn this stuff. Newton, the creator of calculus, didn't learn this stuff, so why are we learning it? Because technically it is important for the subject. Right? Technically you should prove things. Now we don't do a ton of proofs in here, we do some, as we've seen already. You should realize that technically things in math need proof. This is not really the most important kind of proof for that definition of a limit. There are other more important proofs. This is just illustrating how to do the proofs. It's really not the most important kind. Because the function is so simple. It's a nice linear function. Why do you need such a crazy proof to prove such a simple thing? It seems kind of silly in that sense. There are better reasons to do this kind of proof with other situations. So basically, as far as rewriting it in your own words, probably, the first two sentences are the same, but this part, these three, could be a little different. You could choose different words in these two sentences, for example. Maybe you don't look at what you've written down. You don't look at my PowerPoint and try to write in your own words. It's not many words, but you could use alternative words to suppose you could say, if X is satisfying this condition. Okay. Use a little variety. All right, we're almost out of time. Let's quickly, in 2 minutes, look at continuity. You've already learned about continuity. We talked about it as you can draw the graph without picking up your writing utensil. Continuity can be defined in terms of limits. Suppose a function f is defined in the number c and near c, the values of x that are close to c. We say that f is continuous at c if that limit is true. If the limit of the function as x approaches c equals the function value at c. We used this fact already, actually. We used this definition. Back when we were doing the rational function examples in lecture A, when we filled in the hole, the way to fill in the hole was to figure out what the simplified formula approached as x went to c. And we ultimately found those limits by plugging the number in. And the answers we got were like 5/12 and 12/5. I forgot the other example, -5/2. We essentially used the continuity of the simplified formula to find those values. If c happens to be an endpoint of the domain, then you use an appropriate one-sided limit. We say f is continuous on a certain subset of its domain, S, if it's continuous at every point in S. And then I've got some ways in this slide here that I'm not going to show you. I've got some ways that discontinuities can occur. We'll talk more about those on Monday. And this is not the last word on the subject. We can come back to it. This is not easy, okay? But it is fundamental. Even graphs with holes in them are fundamental in calculus, because they come up in a fundamental way in defining derivatives. Graphs with holes in them. Okay? Have a good weekend.